Very good morning to everyone. On behalf of Department of Aeronautical Engineering, I welcome Dr. Muthu Prabhu Elenchezhian from Purdue University, United States of America. We welcome you, sir.
Thank you.
On behalf of Hindustan College of Engineering and Technology and Department of Aeronautical Engineering, I wish everyone a very happy Republic Day. And we have an eminent personality today with us, Dr. Muthu Prabhu Elenchezhian. He has exclusively joined this session from United States of America. Now I may request Ms. Diksha Sambyal to give a brief introduction about our guest. Over to Diksha.
Good morning, everyone. I would like to wish a very happy Republic Day. And we can make a perfect country and can overcome any obstacles in our way. We should remember to raise our voice against any kind of injustice and let everyone know that we are free. Happy Republic Day. So Dr. Muthu Prabhu is a postdoctoral research scientist at Composite Manufacturing and Simulation Center at Purdue University, USA. He holds a MS and PhD in aerospace engineering from the University of Texas at Arlington. Before joining Purdue, he worked as a graduate researcher at the Institute for Predictive Performance Methodologies at the University of Texas at Research Institute, USA, on creating novel method for predicting the remaining strength and life of composite materials and assessing the quality and strength of adhesive bonds in composite structures. He is a cross-functional researcher contributing inventively to the research and development of composite materials and structures manufacturing and characterization methods, performance and reliability systems for composites using combined methods with artificial intelligence, machine learning, and interpretable ML models. He has authored and co-authored more than 30 journals and conference publications, co-authored the book chapter, served as a peer reviewer for various leading journals, and holds a US patent. He also won many scholarships and awards during his career. Thank you so much for joining us today, sir, and we are grateful to have you here with us. Thank you.
Thank you. Shall I start the presentation right now?
Yes, sir. Yes, sir.
Yep.
The session is yours.
Just want, yeah. So good morning, everyone, and happy Republic Day as well. So today, my talk, thank you for inviting me. Thank you, Gopinathan sir, and all the professors for organizing this event. And today, my talk will be on the topic of role of machine learning and artificial intelligence in composite materials. And currently, I'm a postdoctoral research scientist in Purdue University. However, most of this work, the background literature work and everything was carried out in my previous institute, which is University of Texas at Arlington Research Institute. So I'll be speaking about that work as well completely. So a little bit about me. So I did my aeronautical engineering in Hindustan College of Engineering Technology. Yes, I am alumni of Aero Batch 2015. And after that, my final year project was also on composite materials, mostly experimental work. And after that, I started my aerospace engineering master's and PhD from University of Texas at Arlington. My main research focus is on composite materials, smart structures using structural health monitoring techniques, manufacturing and process modeling, durability and damage tolerance, and for additive bonding and artificial intelligence applications. So the outlines of today's talk will be, I will first go through the general introduction and further go through the literature and background of how this work was developed. I'll briefly discuss on artificial intelligence methods, how they are and I have been using them, and focus on sensor technologies that I worked on completely. And with artificial intelligence and for sensor monitoring in structural health monitoring, I perform like 3 different tasks. So I will go over them in like a brief summary of each of them. So uh, just a minute. Yep. So to begin with, as we all know, composite materials, it is made up of 2 or more materials, more constitutively of a fiber and matrix, and it is used in most of aerospace, automobile, industrial applications due to the low weight and high stiffness ratio. There have been many methods which have been developed over the past 2 decades, 2 to 3 decades completely. However, for real-time structural health monitoring, like real-time maintenance to monitor the health of the aircraft structure continuously and to predict what it's going to be its remaining strength or life, or to assess what kind of damage the material has not been completely implemented right now, and it's still an important criteria for most of the aircraft, space systems, pressure vessels, and all the other technology fields. So as we all know, the composite materials has fibers matrix, and it can be made up of different layers like symmetrical, unsymmetrical laminates, and can have different orientations of fiber materials or pre-preg or preforms. So based upon how you change each of these individual properties will actually affect the overall property of the composite material and will change its entire behavior as well completely. So for one such behavior, this is a typical damage mode which actually develops in composite materials. So the plot over here shows the percentage of life, and over here it shows how much damage the material has. So over the percentage of life and structure, that is under fatigue loading conditions. By fatigue, I'm referring to cyclic loading conditions. First, in the initial stage, there's matrix cracking. So between the fiber and matrix, matrix cracking occurs first, and after that, over the duration of the life, the damage develops a lot, and the other 2 stages such as crack coupling and delamination will occur. And further, as it develops, the final fracture will occur at the final stage. And apart from only considering damage, we also consider stiffness, because the remaining strength and as well as stiffness remain at high levels until it reaches the final stages. So based on these 2 plots, we can actually categorize damage into 3 stages: initiation, growth and accumulation, which is the second stage, which is over here as 2, 3, 4 stages, and the final interaction stage where the fracture occurs or the complete failure occurs. So while identifying damage and testing, we need to identify all the 3 stages, and the methodologies need to be developed completely to identify all the 3 stages. So I'll go to some review of literature. So overall in composites, in life cycle of composites or something, the first process starts with design, where we start with either classical lamination theory or material design. And after that, for manufacturing, it can be hand layup technique or Waltham resin infusion techniques, autoclave processes, out of autoclave processes. And right now the advancements, it's in automated fiber placement processes. And in analysis, it goes to CAE analysis and FEM analysis, where you do all the structural analysis and softwares completely. In testing parts, it's with sensor monitoring, non-destructive testing, and sensor monitoring, where you do not damage the entire structure and do testing of the material. And in some cases, for the preliminary testings, you basically do like mechanical testing or fatigue testing of the material, and based on testing you also do inspection and repair. So you analyze what kind of failure or anything is in the material and further develop based upon it. So in all these parts, artificial intelligence are right now being developed and involved to create the entire life cycle in a better way. And So that is how it's focused on completely. I also noticed there's another talk on design of composites in AI this afternoon, and so this particular talk will focus mainly on testing, analysis, and inspection and repair. So testing, inspection, and repair part, mainly on structural health monitoring and how to use the sensor data to further predict the life of the composite material. So moving forward, I will just go through the basic diagnostics and prognostics methods, like what are the sensor systems and how are they available. The most commonly used sensors which are embedded into aircraft structures are like this, and most commonly used are acousto-ultrasonics testing and fiber optic sensor systems. These two are most commonly used by most of the manufacturers. Acoustic emission is also being used, and each of these sensor types has different advantages and disadvantages. That is, not one sensor can measure each and everything, and for each of these techniques you either need a manual, like a human intervention, where someone who has the complete knowledge of sensors and how to analyze the data has to be there to see what kind of results the sensor gives, and hence suggest what methods can be improved. And why do we need artificial intelligence to take part in this composites integration for diagnostics and prognostics? So when you have smaller coupons like this, like a simple cantilever beam or a flat plate or something, you can do a lot of physics with it by making a lot of assumptions. But when the complexity of the structure increases, your complete physics-based dependency decreases completely. So when the entire aircraft sums, most of the assumptions that we imagine in our normal equations do not take place, and more likely the data takes place. So when you have smaller physics, you can do some data calculations and simulations and derive analytical equations. But when there's a large amount of structure and assumptions which cannot be derived completely, you will have a large amount of data, and that's where the data-based learning, machine learning, and artificial intelligence comes into play. So the main method for my research work was to, after we identify the damage and do some assessment based on the non-destructive testing and structural health monitoring, we develop methods which can actually predict what is the residual strength and life of the material. And further, we use the artificial intelligence techniques to take decision actions, like control actions items, on how we can actually control the load, perform maintenance and repair operations in the aircraft structures, and properly send the structure for proper maintenance. So if you see on research side as well as academia side, or on the main point of publication side, earlier from 1990s to 2015 or 2010, the number of articles published which combines on composites, structural health monitoring sensors, and artificial intelligence were completely very less. And only during the past 5 years, the number of publications, that is, the number of research work, has been increased a lot. And even in funding wise, the funding has been increased more for AI developments. This is due to the improvement in the computer technology developments, the capabilities that we have right now. So some previous work, like how other researchers have done to use composite materials with artificial intelligence, are like can you hear me properly?
Yes, sir.
So with composites and AI, other researchers have done like manufacturing and testing services. So during mechanical testing, they collect the data using acoustic emission sensors, and from the data, they actually use vector descriptions of the data. That is, for each and every sample they collect the data, they analyze the data. And after that, sometimes we have a complete label data set. That is, from the data which is being collected by the mechanical testing, we know what is happening behind by the ground truth data. But in some cases, you do not have any ground truth data. In those cases, we need to do unsupervised learning. That is, you will analyze the data by itself and form some data unlabeled database, you will categorize them accordingly into what relates to some point of contour data. And based on that, you will again form a labeled database, that is like supervised learning methods. So based on this, researchers have developed to predict what kind of defect or what kind of damage actually occurs into the composite materials based on the acoustic emission data. Other researchers have also done to use complete life cycle like this, where they pre-process the data, develop some physics-based machine learning models like using Gaussian processes, and try to predict what is the remaining useful life of the system that can be sent to the maintenance repair operations like condition-based maintenance. This is another concept where researchers have proposed to use sensor systems integrated completely, which collects the data by additional wireless sensors, and that actually transmits to the control device, and from that it communicates to the machine learning models completely, so that based on the type of defect or impact, it will be able to say whether the condition is safe or damaged, or what service needs to be taken. So by prognostics, even though there were more methods which were developed on diagnostics, which is like to identify what type of damage it is, there was not much researchers who mainly worked on prognostics. That is, after identifying what the type of damage is, how they want to predict the entire life of the material is. So this was an interesting topic which I began to work on. So as a summary, why do we need to have artificial intelligence for this material state assessment is, as I mentioned earlier, the damage types depends like on damage initiation, damage accumulation, and damage interaction. However, all the SHM tools, they can collect data on the current state of the material, but always need some human evaluation or some other computational model to actually predict the life or something. So by using artificial intelligence on some time dependent models like recurrent neural networks or something, we would be able to actually use the current state of the material, that is what type of damage it has currently, and also observe what is the past behavior, how the material has been performing so far, the previous, if there's any crack developed previously, and how that crack is currently influencing the current damage in it. So this could be possible by using artificial intelligence methods completely. So what's artificial intelligence? I'm not going to go deeply into the mathematical detail, but I'll try to provide an overall overview of the AI examples completely. So in traditional methods like classical lamination theory or any physics-based methods that we developed for FEM or anywhere, we have the theories and we have what input data that we need to provide into the model that we are being developing. And based on that, we develop the codes and model and we finally get the answers. But in artificial intelligence, you actually have the answers like the solution, and you have experimental data, and you do not know what is exactly happening between them. Like you do not know a complete relationship, and you want to establish a relationship between them. So for that particular case, you use the AI models to develop the relationship, and based on that, the relationship which is developed just serves as theory. And even in AI, there are many different types like supervised learning, where you actually provide what the input data and the output data is for the model. And unsupervised learning, in these cases, you provide what the input data is, and you allow the algorithm by itself to find some relationships between the data. In deep learning, it's similar to supervised learning or maybe unsupervised learning, but it goes with several layers of neural networks, like hidden layers, where it tries to establish a relationship. And most of the time, deep learning models are very difficult to understand and study further. And reinforcement learning is like a game player theory. So if two players are playing a game, you remove one player from the game and see what's the contribution of the other player. So this is like you train algorithms completely in a different way. So based on this, you can also develop into different models like statistical AI methods, normal machine learning, which I spoke about earlier, and there are also evolutionary computational methods like genetic algorithms and other things. And my research and this presentation will mainly be focused on the machine learning, that is purely data-based algorithms completely. And apart from the AI part, the AI part of development has been done for the past 5 to 10 years. However, the current interest of what comes into research field is about interpretable machine learning or explainable artificial intelligence. So let's say you develop an AI model and your AI model predicts a particular value, that this is going to be a life, or this is going to be the strength of the material, or some other model that you develop for your own project or own case. So why did your model predict that particular results? So you need to be answerable on why that particular decision was made, or what kind of data made that particular decision. So that is one of the interests, and this is mainly important because most of the companies or industries right now develop AI models for space applications and critical domain applications, but for these you need to have certifications. Without certifications you cannot proceed further, and to achieve further certifications you need to be 100% sure that your model is completely accurate in predicting, or at least like 99% sure, because it involves a lot of cost and lives as well. So this particular concept has been recently developing mainly for composite materials. I haven't seen hardly more than 10 to 20 papers on this topic completely as of now. So this is an emerging research field as well. So in this presentation, the models that I have used mostly are like linear regression, where you directly establish a relationship between input to output variable in a linear manner, and logistic regression. I have also used random forest. It's kind of like a decision tree algorithms, where you can use it for either classification or regression. So in decision tree algorithms, you build a number of AI models and you allow the algorithm by itself to predict the outcome of the model. Similarly, I'll go through in detail for artificial neural network and long-term, short-term memory models, which is a type of recurrent neural network models during the work. So for a neural network model, the simple example is like input to output mapping. You have number of inputs over here, and with these number of inputs, you need to map to this particular output over here. So you design a layer, or you design some in between layers completely, and those layers assign some weights into them. So the output will be calculated based on how the weights are being generated, and randomly the weights are being assigned in the beginning, and further it gets developed to predict the output. I'll explain this with a simple example, and many of you might have already seen this example if you had already taken Professor Andrew and Jay's machine learning course online in Coursera. But for those who haven't seen, this is kind of a basic example that makes us understand the concept more clearly. So this example is about the AND gate. All of us have learned what AND gate is and know how it works. So over here, what we are trying to do is the AND gate basically has two inputs, x1 and x2, and the output will be y, which actually does the AND operation for x1 and x2. Now we are trying to generate this as a neural network model, or like a simple linear regression model. So over here we have same x1 and x2, and we have a bias term which is 1. And now we need to assign some weights to it. And the weights, let's say it's 20, 20, and minus 30. So once the weights are assigned to us, we need to calculate what's the output, and it is calculated by a function. So g of minus 30, which is this value, into the complete term over here. So this is the function which has been calculated, and based on this you have an activation function. Over here what we use is a ReLU activation function, and there are many other activation functions that can be used completely. So what this set is, if g of this particular value is greater than 4 or negative 4, then the value, if it's greater than 4, then it corresponds to 1, and if it's lesser than negative 4, then it corresponds to 0. So based on what this value develops, we would be able to produce the output, which is actually for the AND gate. So this is a very simple basic example of how a simple one layer or one layer neural network model can be developed, and most of the artificial intelligence developed based on these but are too complex based on how many layers you use, what kind of optimization algorithms we develop and we use for them, and how we actually generate the entire models completely. And mainly depends on what data you have and how your data development is. So the basic steps for this artificial intelligence models are like, first we will pre-process the data, that is the data cleaning and normalization. And sometimes you have uneven data, like the total length of the data might be non-uniform. So in those cases, we used to do data padding, that is we make the data to uniform length. And after that, the total data set will be divided into two different sets as training set and testing set. In most of the cases, 80% of the data is being used for training and remaining 20% of the data is being used for testing. And with the training test, you can actually do a cross validation test. That is, this 80% of the data goes into cross validation, and that is you can do a like a 5-fold or a 10-fold cross validation. So during each development process, the number of training and cross validation test changes, and based on this, multiple developments are done completely. So you can do the hyperparameter tuning. So this is how a basic AI model is developed. So now moving forward, I will say what will be the main focus of my work, which I did earlier. So I want to implement a complete real-time prognostic system where you actually place the sensors in the aircraft structures and you develop a cloud-based monitoring system where you can actually, by the aircraft's tail number, you can observe what kind of sensor data the aircraft collects in it. And based on the cloud, you can see its material properties, manufacturing data, like how it was manufactured, how many times it was serviced, and what was the previous material condition. And by the real-time sensor, you actually collect what is the current material state. And based on that, the AI model will predict what is going to be the structural airworthiness of the aircraft. That is the aircraft very safe to fly, or when does it need to go to maintenance further, or what needs to be done next for the aircraft, whether it can, after how many days or how many months or how many years it needs to go for a maintenance, so that it can be scheduled accurately and proper maintenance can be taken care of. So next I will go with the sensor technologies which I worked with. I'll be introducing a concept called broadband dielectric spectroscopy. In most of the places, this is called as electrical impedance spectroscopy. So what this electrical impedance spectroscopy and how it works is, it works by the interaction of electromagnetic waves with matter that and reflects by the underlying molecular mechanisms. So basically in composites, it's made up of fiber and matrix, and the fiber and matrix actually, when they bond to each other, they form an interface between them. So when this electrical charge is passed between the actual molecular structure, there undergoes some polarization mechanisms within the composite material itself. And based on that, we'll be able to capture what kind of what is the quality of the material, or what kind of damage the material has in it completely. So how this testing is done is, the dielectric material, which is actually the composite, it's placed between two conductive plates and a small amount of current is passed to it. And based on this, all the dielectric properties such as permittivity, impedance, conductivity, and capacitance are measured in it. So we do this test when the actual material is in a good state after manufacturing immediately, or it's a pure material, and continuously the test is done at often times. So based on how the property changes between the initial state and later state, the actual difference between them is completely obtained. So based on the relationship between the final state of the structure versus the initial state of the structure, that is the relationship which will be correlated to other patterns. So this technique is not very popular, but it's been developing completely. And my research group, which I worked earlier at UT Arlington, we have been developing this a lot completely. And based on this, we did a lot of work. So the blue curve over here represents a normal stress strain curve, which has been obtained by the MTS mechanical testing machine. And the red curve, which over here represents the normalized permittivity values. That is the permittivity value with reference to the initial value. So as we can compare these two curves, we could actually correlate them into three different stages based on how the rate of the red curve develops. And this is correlated to what kind of zone 1, zone 2, like what kind of damage mechanisms it happens. And this test was particularly done for like 50 samples. And on most of 50 samples, what was observed was that if the mechanical property, that is the strength of the material, if the mechanical property was higher, then the dielectric property which was observed was completely lower. This is compared to the average values of the mechanical properties and dielectric properties. Also further, we also do adhesive bonding, where you actually bond the composite structures or even metallic structures. Most of the aircraft structures, helicopter blades that are used in the rotor blades, they do not use stiffeners or other joints, and mostly use adhesive bonding because of the stress concentration factor. However, the weak point of the adhesive bonding is that it has a kissing bond or like a weak bond, and they need proper methods to analyze them. So we use this broadband electric spectroscopy to make different type of defective samples and compare them. And based on the comparison, if the actual shear strength of the adhesive bond increases, what was observed was the dielectric property was decreasing completely. So this was one of the methodologies that I used for most of my research work and for my PhD dissertation as well. And the other sensor technology that I used commonly was fiber optic sensing system. So the fiber optic sensing system is similar to our optical fiber internet cables, and most of the fiber optic sensing systems works by the principle called fiber black ratings. So basically, when you have in the initial stage, you will have a particular black rating, and when the fiber is elongated, that is when any kind of load, either thermal or mechanical load is applied, the fiber stretches and the black rating moves. So based on how much the black rating moves, you can actually calculate what's the temperature difference or what's the strain difference that the material is actually undergoing. And this has been a very popular application currently used in aircrafts and space research as well as for civil and industrial applications as well. So over here you can see a bridge which has been planted in one of the rural villages here in USA, in Tennessee. And this bridge is completely made of composite material, and it also has fiber optics implemented into it completely, and that's a monitoring system. So this completely monitors how much load the bridge experiences during the entire time. Also, it can also be used to track whenever the vehicle crosses the bridge. So based on whenever the vehicle crosses the bridge, that's a load which has been observed on the bridge. And in future, this can be implemented into complete aircraft structures by placing fiber optic sensors. As a demo concept, most of UAVs right now started using fiber optics to see what is the strain deflection during the actual flight, during takeoff and landings and such. And another advantage of using fiber optic sensors is that the optical fiber sensors can be placed completely during the manufacturing. That is, during layup, you can actually place the optical fibers into the entire composite structure by itself. And the strength of the composite hasn't been found to vary a lot based on this. So after this, during curing, you can also monitor based on temperature and flow how good the composite curing is. And in operation, you will be continuously monitoring what is the real-time health and strength. So this is all the basic introduction, and I will move forward with my actual research work, which I have done completely. So this will show the actual examples which I performed based on the studies which I have done. Excuse me. So the first research task was performed to actually assess the defects in composite materials. So I made 4 different composite panels and artificially induced defects in them, like using a release film, using backing paper, and using release paper. And based on this, we actually did the broadband dielectric spectroscopy measurements. So if you imagine what the actual panel manufactured will look like, it will look like these different images with different defects in them completely. So based on this, we collected a complete data set, and the data set was for total of 256 samples. We had 4 different classes, so 64 data points for each class, and all of them are the 14 dielectric properties. And this 14 dielectric properties were actually collected at different frequencies from 0.1 hertz to 1 megahertz, that is during the entire dielectric spectrum. And after that, we did a Pearson correlation analysis to analyze the correlation between dielectric parameters, and it was completely reduced down. And only the limited data set was used for the complete analysis. So first thing that we always do with data is to visualize the data to see if we can actually physically see any relationship between them. So in cases of the different features that we had for the entire data set, we actually differentiated them into different classes. So over here you can see, you can really identify few of the defects completely, like it belongs to each different class based on how it kind of it was based on the data. So further, if you develop the machine learning model or AI model, you'll be able to accurately define, because by visual you can just see 2 different features, but over here you had almost like 47 or 48 different features which I used in the final model. So we developed 4 different models, like logistic regression model, because it's a classifier algorithm. And after that, we used a random forest classifier, artificial neural network model as well. And these are the confusion matrix. So what the confusion matrix does is it predicts what's the true label versus what's the predicted label. That is the ground truth data versus the actual predicted data from your artificial intelligence model. And all the 4 models developed were pretty much having a good tested accuracy, and the artificial neural network model over here had the highest accuracy for this. And as I mentioned during my previous slides, I also wanted to see what is the interpretability of these models being developed. That is, I wanted to know which feature actually contributed to predict the output of my model. So to analyze that, we can do permutation importance. So what permutation importance does is it artificially changes the values of the feature, and based on that, it predicts the output of the model. And based on how much the error percentage changes, the weight for each individual feature is being obtained. So in all the 4 models being developed, we can see the lower permittivity, that is the 0.1 hertz real permittivity, or the imaginary impedance values, were the most contributing features for my model completely. Another task for the interpretability machine learning as well, researchers have developed a concept called LIME, and based on this, you will actually be able to obtain similar results. Like you'll be able to predict which particular feature contributes to how much of which class of prediction completely. So for the all 4 models being developed, it was identified like the conductivity values over here and at the low frequencies were completely predicting to the complete final prediction. So based upon different algorithms or different techniques that you use, your predictions will completely vary. So the main goal of developing the AI model is completely validating it. Like you need to be sure which algorithm gives you the most accurate results and reasonable results completely. And another technique for interpretable machine learning is SHAP. It does the same thing, but it does by another method. And in SHAP, you can actually do the global prediction. That is, the identify which total features contribute to the entire model's prediction as a SHAP summary, as well as you can do local prediction. So let's say if the model predicted that your defect is going to be the third class over here, then that is the backing paper class. Then you can say for this backing paper class, which has the highest value over here, as in all the other three models as well, which particular values contributed to them most. Here you can see it's the real permittivity at 0.1 hertz and the conductivity value is 2 hertz. So and one thing which you noticed is different model gives different results. So it's more important to validate it in a further state. The next task I'll be speaking about is about how to identify the damaged state completely. So how we started this work was actually, we first took a physics-based equation similar to the AND gate example. We actually took the relationship to obtain the knot strength of the composite material, sigma n divided by sigma naught. And the knot strength of the composite material is basically developed based on three input factors, which is KT, A naught, and R. So based on these three values, we have a physical relationship which has been established, and we generated an artificial data set, like developed some input, random input values for all the three parameters, which is obtained from statistics, like the literature as well, and developed the data set. And since this data set is completely developed from a physics-based equation, the accuracy prediction of the model, the R-square score of the models are very high. It's more than 99.8% in both the cases. And with the random forest regression, you can also identify what features contributed to the output prediction of the model. And the main goal of this work is that apart from experimental data that we are developing, just using the data to develop the actual output model, if we use some physics, a known physics in between them, when there's a large amount of data involved, you will be able to develop a complete hybrid model. And this hybrid model will be able to develop the result more accurately and lead to the final decision-making process completely. And in the experimental side, what I performed was that we did some quasi-static testing of 4-ply off-axis composites. And these were tested as per the ASTM standard in MTS. And during this, we actually collected the dielectric data during the quasi-static testing. And based on that, the results that we obtained was that this is the fractured sample. And so this is the stress strain curve as we showed earlier, and this is the dielectric relationship curve. So we obtained what is the first slope, which is the rate of the change of these curves. And again, the second slope for the this curve, which is the acceleration of the curves. For this particular example type, remember this is for this quasi-isotropic sample over here. So for this particular example type, we can see that we can identify the characteristic damage state point, which is where the actual stage 2 occurs. And we can, from the second slope curve, which is the acceleration curve, we can identify where the actual damage actually accelerates completely. So this is based on like a quasi-static testing, and we collected a complete data set. And in this data set, this is for different samples, like 11 different samples. The sample set is still small. We collected what is the actual dielectric value versus time, and obtain what is going to be the first slope of the values versus time for this curve. And we wanted to predict, given the real permittivity values, we need to identify what is the first slope value. Because the point at which the first slope value crosses 0, that is the point at which it changes from positive to negative, is identified as the characteristic damage state point, that where the actual stage 1 changes to stage 2. So since the data set is of ununiform length, we need to actually do padding, so to make the data uniform. And after that padding, after we make the data uniform, we can classify them into different batches. And based on that, we developed an artificial neural network model, as well as a random forest regression model and recurrent neural network model. And these are the properties for the model that I used completely. So seeing the results, the actual long-term, short-term memory network, which is the recurrent neural network model, had the best prediction accuracy. And this is the output from the random forest regression. In random forest regression, we'll be able to obtain feature importance where we can see which features, like at which point most of the accuracy predicted. And this is the results for the machine learning neural network model. Here we can identify that the prediction was close to identify at the point of zero while the actual characteristic damage state occurs, but the overall trend varied a lot completely. However, in the recurrent neural network, which is the LSTM model, the prediction was also more accurate, and the overall trend matched a little bit better compared to the normal neural network model. And the final task which I performed was to actually do it under fatigue load, that is under cyclic loading conditions. So in this case, we actually did mechanical testing under fatigue loading conditions for the samples. And in this, we collected the dielectric data, and simultaneously, we also collected the fiber optic strain data and developed the AI model, which can actually predict what is the strength and life of the material is completely. So a similar kind of test was done. Over here, if you can see, this is the fiber optic sensor which has been connected to the actual MTS testing machine. And this is how I bonded them to the actual composite samples. And this is the quasi-dielectric sensor which has been connected to the testing. So first thing, what we performed is did the quasi-static test, and from the quasi-static test, that is under normal static loading conditions, we obtain what the ultimate tensile strength is. So the ultimate tensile strength was obtained to be 314 megapascal, and we did some statistical analysis on what the maximum and minimum value can go to, and based on that, we determined to do fatigue test at 3 different load levels. That is at 50%, 25% and 75% of the load cycle with different R ratio values. And for each conditions, first we ran a complete test where we actually did collect the number of cycles to failure for each of these different load conditions. So if you see, these are the mean cycles to failure for the 3 different load conditions, and under fatigue, composites will have different values. Like one sample will fail at 10 cycles and another sample will fail at 500 cycles. That's a common property of composites. So you need to always do a lot of samples to get more number of data. And after that, I did some more tests to identify what are the residual strength, that is the remaining strength of the material. So this is a typical pattern that we did for the fatigue test, where we load up to a certain level and do fatigue for a limited number of times and then ramp it down. And after some time, we do, after the cycle has been done, we pull it up till failure to know what is the actual remaining load of the material. And this was the mechanical response which was applied based on strain. So this is the strain values. And this strain value is again compared to the dielectric response value over here. So this is the data that we got from the dielectric. This is during ramp up. This is during the fatigue curve. This is during the unloading curve. And this is during the second ramp up and during failure. And different residual strength values were obtained for the 3 different loading conditions. So how I actually use this data is that we again first obtain what is the first slope and second slope values. So we have the stiffness curve over here, which is normalized, which is the black curve. And we also have the dielectric property curve, which is the permeability curve over here, which is shown in the red. So once you can see almost at 80% of life or after 75% of life, the permeability curve actually shows a reduced behavior over here. But the stiffness curve is still straight, as you can observe directly. So by obtaining the first and second slopes for stiffness, you can see the black curve is the first derivative, first slope, and the red curve is the second derivative. And similar curves were obtained for permittivity as well completely. For the red curve is the second derivative and the black curve is the first derivative. Comparing both in the same figure and normalizing the values, the red curve shows the stiffness curve and the black curve shows the permittivity curve. That is, that the permittivity curve were able to predict the failure in the material well earlier than the final failure actually occurred. That is, the failure in the stiffness curve was obtained at 75% of life, but the permittivity data was able to predict almost at 70% of life. And this is for one particular loading condition of fatigue. And the same behavior was obtained for the other two different loading conditions of fatigue as well, under 25% and under 50% mean stress levels. So based on this, I actually use this input data where we have the actual permittivity over life and also the strain over life to develop AI models. And in AI models which I developed, I actually developed it based on predicted the output by giving different time steps of data. That is, you need to make real-time predictions. You won't have the entire data set to make the complete predictions. So first, you give only the first 100 time steps of data and leave all the other data to be 0 or padded value of 1. And you see what the predicted output life is. And as you get more data and information about the material's health, you provide more data and information to the actual structure. And as you slowly provide more and more data to the structure, your prediction accuracy gets increased completely, because as we saw from the damage behavior as well, you do not know complete damage state or complete damage behavior in the beginning itself. You will mostly know accurately when it's about to end, almost at 75 to 80% of your life. And that's a typical behavior of composite materials. So this is what we observed when we use permittivity as the input. But this was not the case in strain, because the strain data was completely close to each other for all the different time steps, even if you have more predictions. So with the strain data, we were able to get more closer predictions because the strain data had the same uniform behavior completely, but the dielectric data did not have a more uniform behavior in the overall response. So, yep. So this is a complete research work that I have done so far by using the sensors for prognostics. That is, we need to use some prognostic techniques completely that we can actually predict what's the remaining residual strength in life, and use the artificial intelligence algorithms. And these artificial intelligence algorithm needs to be developed in such a way that they can be adaptive, like can be used for any different composite material or for any different robustness to other material configurations, and also needs to be having some kind of physics implemented in them. Also needs to account for the uncertainty, that is how interpretable the actual model being developed is. Yep. That's it with my presentation.
So thank you, sir. Thank you for your wonderful presentation. Now shall I? Hello, sir.
Yeah, go ahead.
Yes, sir. Thank you for the presentation, sir. Now the session is open for the participants for questions. The questionnaire session is open now. So the
Sir, good morning,
audience
sir.
yes.
Sir,
Audience
good
may
morning,
unmute your mic.
Sir, good morning, sir. Any good paper, sir, on this to refer? I am a beginner for this.
Regarding, are you asking papers regarding artificial intelligence or regarding the prognostics or composites?
Prognostic of composite.
Yes, I can actually share the papers with you actually. If you can actually message me on LinkedIn or email me directly, I will send some papers on this topic completely.
So, do we have review paper, sir?
Yeah, I have itself published a review article on this topic. The first few slides which I presented was from a published review article.
It includes artificial intelligence also, sir?
Yes.
Sir, any good course on this artificial intelligence, machine learning, sir? Any good course?
So when I started my PhD, I also did not have more knowledge on artificial intelligence stuff completely. So I took the machine learning course in Coursera, which is from Stanford University. That's a basic course which everyone can take, and that is really good actually.
Okay, sir. Okay. Thank you, sir. Thank you.
Yes, sir. Any more questions, sir? Sir, since the participants are asking for your contact details, can I share the mail ID, your official mail ID here?
It's in the slide is still displayed, right?
Yeah, it is there. And also, can I put it in the chat box also? Muthu Elen.
Yeah, sure.
Purdue.edu, and you have given your personal ID also, right, sir?
Yeah, either email should work fine. I'll respond in anything. That should not be a problem.
Okay, sir. Okay, thank you. The participants can make a note of it. You can note down SAR's mail ID in case of any further doubts. You may directly mail him. Apart from that, if you have any other doubts here, you can. So there is one more question that please share resources on prediction using ML, machine learning.
Yep.
Mr. Chandra Kumar, are you here?
Yes, sir. Yeah. Thanks for the nice session, sir. Yeah, I will contact through LinkedIn, sir. Thank you very much.
Okay. Yeah.
Okay, thank you. Any more questions from the participant side?
Sir, another thing, sir. Sorry to disturb, sir.
Yeah.
That codes, can we get, sir, your this thing, some machine learning codes? You talked about regression, what you call artificial AI, and decision tree like that, sir.
Yeah, I will try to send course links as well. And I don't have the course materials with me, but I can see from LinkedIn, like there are some open books and notes which can be easily read. I'll try to share that material as well during the
No,
email.
sir. Code, sir. We have to use the code, no, sir, for this regression and other things.
For all my research work, I actually used some open source codes only by sklearn or something, and they are more likely you can use it directly from them.
Okay, sir. Okay.
Is there any more questions from the participant side? You may either unmute your mic or else you can drop a message in the chat box.
Hi, Muthu.
Yeah.
This is Saranand, sir. I hope you
Hi,
remember
sir.
me.
How are you?
Fine, man. So I'd like to have 3 questions. So my first question is that how about assessing the material using image processing methods? Since with the some sensors are may tend to failure sometimes.
So during image processing methods using artificial intelligence, many people have done work using convolutional neural networks.
Yeah, okay.
And sensor failures are prone to occur even with even with autonomous cars and robots which developed, they actually map by capturing the actual image processing. So if there's a sensor failure occurring, there are some methods needs to be developed how to overcome that completely and work based on it, or completely make a solution towards it. But while you actually develop the data set for image processing, you collect the data completely and train the model based on how the data is completely. So you do some data augmentation, that is introduce some noise into the data. Like you do not always use proper images and have some like smugged or little bit damaged pixel images, so that your model gets trained on that particular data set as well.
Okay. Thanks
But
for that.
complete sensor failure is another issue to be dealt with, the uncertainty part.
Okay. So my second question is that how about this machine learning models are going to interact with this environmental effects?
With the sensors?
Since our AI model and machine learning models are going to be very ideal, right? So they are not going to include any environmental effects, right? So how we are going to include that environmental effects? Because those are very difficult to predict weather conditions, the environment is going to, the materials are going to.
So right now
adapt
when I did all my experiments, we do the experiments in the data completely. We do the experiments in the laboratory scale completely. So in laboratory scale, you'll be actually able to collect more data. However, while you are developing these models for actual implementation, you use the data which is some actual maintenance, like what data it's been collected in real time, or you create a data set which can actually include all environmental effects based on computational like simulation techniques to include all the effects completely. So this data, like the model that you develop in laboratory scale needs to undergo several processes to be completely implemented in real time for the aircraft.
Okay, that means we need to create a separate model for all those things.
You can actually use transfer learning where you have more data based on your laboratory scale model and train on limited number of data which you get from real time and retrain the model based on it.
So how about this? So like machine learning and artificial intelligence are like progressive models. How about the regression models, like learning from the cracks? Is it possible?
Learning from the cracks based on the sensor data, right?
Yeah.
Yeah, that is possible as well.
Okay.
Based on
Yes.
yeah, like based on regression techniques, like my research work mostly dealt with actual data, like from the based on these two sensors alone, which is the dielectric and fiber optic sensors. But there are more articles where they actually capture the crack images and predict, develops computational simulation models, as well as conclude, as well as correlate them with the machine learning models. So they compare how the crack development is and predict what will be the final failure of the crack, or how much the crack will develop completely.
Okay. So the final question is, so what is the kind of programming languages for writing machine learning models for this kind of fracture analysis?
So most of the people actually use Python, because Python is open source completely, and you can publish the codes in GitHub or use it for publishing papers. And nowadays, most of the artificial intelligence codes are open source by using the Python libraries like scikit-learn or any PyTorch, TensorFlow or anything. So they are open source and easily able to modify, and they can be used completely. Some researchers use MATLAB. However, MATLAB, it's a commercial software, and you have all the rules and restrictions when you are publishing or developing a software using MATLAB completely. So the preferred one that most of the researchers use for sharing open source and for publication is Python.
Okay. So in regarding mathematical model development, so what is the idea? Is this PDE or which kind of equations are necessary to learn to adapt the equations, like converting equations into programming?
That completely depends on the model type. Like in one of my slides, I showed like you have 3 different modeling capabilities. One is like direct machine learning, where you have database like supervised and unsupervised. Another thing is like probabilistic machine learning, like it depends on PD. Like you can use like Gaussian networks, uncertainty equations, and other PD algorithms. So it ultimately depends on what kind of model you want to develop. Like the using PD equations completely relates to Bayesian models or physics-based machine learning models, because they are more certain rather than purely data-dependent models. So it again depends on your application, what you want to achieve finally.
Okay, thanks, man. Nice
Yep.
talking to you.
Yeah.
Have a great future ahead.
Thank you.
Hello. Yeah, thanks for
Yes.
the nice session again, sir. Sir, can open source software such as Vika, etc., are available? Can those be used, which are relatively easy for beginners?
I guess yes, but I haven't used Bika myself personally, so I'm not sure about it. But all open source softwares are easy to learn. Like earlier when I started, there were only paid courses online in Coursera or in many other websites. But right now there are a lot of YouTube videos, like playlists, which actually teach us complete artificial intelligence for beginners from start to scratch. Like there are like 2 days program or 3 days program which completely teach artificial intelligence. So those courses also show what kind of softwares which are open source, which are available, you can use. And many of them share their codes like GitHub codes or open source codes so that they can be reused completely. Just a caution, if you are using those codes for publications, make sure to cite them completely. So other than that, basically you can use them and modify it based on your input data and your work. So you can modify the model accordingly and develop your model, because whatever codes, even though you use same kind of codes from the other open source, at the end of the day, it depends on what kind of model you are developing, what's your input data and output data, and what's your like the hyperparameters or what architecture of your model basically.
Yeah, thanks. Thank you, organizers, also for bringing such a good session.
Yeah, thank you, sir. You're welcome. Any more questions?
Regarding Birasal's question, a few insights of fiber optic sensors over AE sensors. Both the sensors have their advantage and disadvantages. One thing that I can readily say is with AE sensors, you have huge equipment and it takes a lot of space and implementation for installation. With fiber optic sensors, it's more easier to install and it does not affect the quality. Like for real-time monitoring using AE sensors is very difficult. But with fiber optic sensors, it's a very small fiber which can be embedded into the complete structure. So that's the main point.
Okay, thank you. Any more questions from the participant side? Please, you may unmute the mic and either you can unmute or you can drop a message in the chat box. I think that's it from the participants. And the resource person has shared his contact details in the slide. You may note it down. In case if you have any doubts, you are free to contact him through the mail ID, through the mail conversation, or else through the LinkedIn. He will be available for you. And now, thank you very much for being here, Dr. Muthu Prabhu. And it is, I would like to convey my sincere gratitude and thanks for being here, accepting our invitation, and despite of the huge time difference and your busy schedule, you are here. So thank you very much. And indeed, it is our pleasure to inform the participants that he is our proud alumni of Hindustan College of Engineering and Technology. Thank you for being here, sir.
Yeah, thank you.
Yeah, thank you. So thank you, participants, once again. Hope you have enjoyed the session. I hope you have learned a lot of things from the resource person, and his contact details are here in the chat box. You may contact him in case if you need anything regarding artificial intelligence or machine learning. And don't forget to join the afternoon session. We have another eminent personality who is going to join from United Kingdom, and his details will be in the screen in a minute. The afternoon session, so we will, due to some sudden change in the schedule, Dr. Satish Kumar Anusia Ponuswamy couldn't able to join from UK. Instead of him, Dr. Ammasai Sengodan Ganapati from University of Salford, Manchester. He'll be joining us for today's session. He's also joining from United Kingdom, whereas Dr. Satish Kumar Anusia Ponuswamy, he will be joining us for tomorrow's session. So there's a small change in the schedule. Instead of Dr. Satish Kumar Ponuswamy, Anusia Ponuswamy, Dr. Ammasai Sengodan Ganapati will be joining us for the today's afternoon session, and his topic will be high growth thermal effects on the translaminar fracture toughness of composites, and he'll be joining from University of Salford, University of Salford, Manchester, and we are happy to inform that he is also our okay. Okay. And we are happy to welcome our former head of the department, Mr. Adak sir. So we welcome you, sir.
Thank you so much. I'm not well, but I just want to have look at my ex-student, but I missed him,
Yes, sir. He just completed his session.
Yeah.
Oh, yeah, he's here, sir.
Hello,
He's
sir.
here. He's here.
How are you?
Okay. Oh, fine. Very nice to see you and doing great, great. It's
Yes,
a
sir.
lot of blessings from me, a lot of blessings for you. Okay,
Thank you,
right?
sir.
I'm so proud of you, Okay, right.
Yeah.
It's an excellent, arrangement done by my department. Okay, and with Gopi and everybody, all the faculty members and the staff, and it is excellent. And I'm so happy. I'm not well, but I wanted to see you. Okay, I missed it. I missed it. Anyway, better luck
Yes, sir.
next time.
Yeah,
Have
nice
a
to meet
great
you
day.
too, sir.
Hope your
Yeah.
family is okay and all that,
Yeah.
etc. Okay, fine. God bless you.
Thank
God
you, sir.
bless you. Okay, fine. Okay, go ahead with the topic.
Yes, sir. Thank you, sir. Thank you. So, dear participants, for the afternoon session, we'll be having, instead of Dr. Satish Kumar Anusuya Ponnuswamy, previously that was our schedule, but unfortunately he couldn't able to join us today. Instead of him, he will be joining us tomorrow. He will be joining us tomorrow for the afternoon session. Instead of that, Dr. Ammasai Sengodan Ganapati from University of Salford, Manchester, he's going to join us for the afternoon session, and the topic, it is in the screen. So I request the fellow participants to join for the afternoon session. I hope you will not miss it. So I'd like to see you again by 2:30 p.m. sharply. And thank you for being here. And once again, on behalf of the Department of Aeronautical Engineering and Hindustan College of Engineering and Technology, I wish all the participants a very happy Republic Day. Thank you very much for being here. Thank you.